So, we're going to continue on looking at motion. We are now familiar with Newton's second law. The net force acting on an object equals the mass of the object times its acceleration. So if you have a net force acting on an object and that net force is not zero, then you have an acceleration. Your object will accelerate. That means it may either speed up or slow down or change direction. It just depends upon how the forces are applied. I'm going to modify this ever so slightly. If you remember, acceleration is the derivative of the velocity with respect to time. I'm going to put that in place of acceleration in our force equation. Now the problems we're going to look at, the mass of our objects is not going to change. So our object's not going to be gaining mass or losing mass. We'll talk about different objects interacting with each other, but the mass overall is the same. So if mass is going to be a constant, is it fair to say this? If we take the derivative, the mass just comes out anyway. So I can write it in the derivative or not in the derivative. This quantity, mv, is called the linear momentum of our object. The symbol we use to represent linear momentum is a lowercase p. It is a vector because velocity is a vector. Momentum is equal to mass times velocity. That means an object at rest has no momentum. If v is 0, momentum is 0. But an object moving will have momentum. How fast it's moving and how massive it is will determine how much momentum it has. Okay? Momentum is nice in that it's able to distinguish between, say, a semi-truck and a little car driving down the freeway at the same speed. They would not have the same momentum because semi is obviously more massive than a small car. So momentum actually is a nice way to look at some of our motion problems. So we can write this equation here. Net force is equal to the derivative of the momentum with respect to time. So the net force is the rate of change of momentum. The bigger the force, the bigger the rate of change will be. Okay. Another way to look at this too, if you have a net force, your momentum has to change. If this is not 0, this cannot be 0. So if you have a net force acting on an object, the momentum of the object must change somehow. Okay. Now if we take this equation, I'm going to bring the dt to the other side and integrate. It's an equal sign. This, when we integrate force with respect to time, this is called impulse. Everyone's familiar with impulse, commonsensically, not just necessarily in the physics terms. For example, let's say I had to change a light bulb. So I jumped on the table, I changed the light bulb, I want to get it down, so I jump off the table. I have two options. I can jump, hit the floor, and let my knees bend as I land, or I could jump off, hit the floor, and lock my knees when I land. Unfortunately, we probably all had this experience. It doesn't feel good to lock your knees. What's happening, if we integrate this side, integral of dp is going to be momentum final minus momentum initial. We can't integrate the left-hand side unless we have a function, though. So I'm going to leave it as the integral of force with respect to time. Jumping off the table, my final momentum, we're including hitting the floor and coming to rest. So my final momentum will be 0. My initial momentum would be the momentum right before I hit the ground. Okay? So we could figure out how fast, because we know how far I'd have to jump off the table. We know the mass of a person. So we could figure out the initial momentum. Whether I lock my knees or let my knees bend, momentum final is still going to be 0, because I'm going to come to rest. And momentum initial is still the same, because I'm traveling at some set speed before I hit the ground. It doesn't matter if I lock my knees or not. I have the same initial momentum. Okay with that? So according to this side of the equation, no matter how I land, this is going to be the same. Which means this side has to be the same. So the total integral of force with respect to time has to give us one set value, regardless of how we land. The difference comes in these individual values. If I bend my knees as I land, it takes a little more time for me to come to rest. If time is bigger, force has to be smaller to keep it the same value. Okay? So basically, you're minimizing the impact force. The longer you take to actually come to rest when you hit the ground, the force of the ground on you will be less the more time you take to actually stop. That's why bending your knees doesn't hurt so bad, because the force is less. If you lock your knees, you have to come to an abrupt stop. You have very little time, so the force is quite large. That's why it hurts. Okay. You've probably seen this in terms of a pole vaulter, for example. Pole vaulter, run, 6 pole on the ground, flies over the bar. Well, they have a big foam pad there for them. They don't have to put the foam pad there. Either way, their momentum's going to change. They're going to come to rest. But they certainly would prefer the foam pad there, because the foam pad takes more time to stop the person. The more time it takes, the less force is applied to do it. So the impact force, again, is smaller. Okay. That's why they use airbags in cars. Now, they can hurt too. They're still quite intense in terms of their forces. But it's better than hitting, say, the steering wheel that has no give at all. So the impact time, anything that gives, the time will take longer to change the momentum. Therefore, the force will be smaller. Okay. It's also why gymnasts, on their floor exercises, the floors are spring-loaded to minimize impact when they jump and do their flips and whatnot. Can you think of an example where we would want the opposite to be true? A small time so we get a big force. Hammer, hitting a nail. You don't take your sweet time touching the nail with the hammer. You gotta, boom, hit it hard. Short time to get a big force to get that nail into the board. Exactly right. So impulse. The symbol your book uses for impulse is a capital J. Impulse is equal to the integral of the net force with respect to time. But the net force with respect to time is also equal to momentum final minus momentum initial. So momentum is also equal to the final momentum minus the initial momentum. Remember, final anything minus initial anything is change. So we can say the impulse is also equal to the change in momentum. So two equations. These two are equal to each other. Since they both relate to impulse, they have to be equal. The integral of the net force with respect to time is equal to the change in momentum. If you want to talk just about average forces, you can write this as the average force times however long it took for that impact to take place. And that will equal the change in momentum. So graphically, if I had a graph of force of something versus time, say the force of a ball hitting the floor, so the force of the floor acting on the ball, it would look something like this. The force is not constant as the ball collides with the floor. It will increase and decrease as the ball collapses and rebounds. How would I find impulse if I have a graph of force with respect to time? Since impulse is the integral of force with respect to time, we know integral graphically is just the area under the curve. The impulse is simply the area under the curve. So if you have a force versus time graph, you can find the impulse and work backwards and find momentum, for example. Okay.
What was F and I again? I mean, what was I? Initial.
Yeah, final and initial. The nice thing is looking at momentum and impulse here, it allows us to relate velocity directly to force and to time. It's equivalent to what we've done already, using a kinematic equation to find acceleration and then acceleration to find force. But written this way, it's now a direct link between force and velocity. So kind of gets rid of the middleman stuff. Now momentum. It turns out momentum is really quite useful in situations like crashes, collisions of some sort, whether it be car crashes or playing pool, the balls colliding with each other, or bowling, the balls colliding with the pin, or the ball colliding with the pins, I guess I should say. If you have a system of objects, for example, let's say we have a car, mass 1, traveling at some initial speed. So V1 initial is the speed at which car 1 is moving at. Now, it's moving to the right, so the velocity would just be V1 initial I had. But I have a second car. Also traveling to the right, but not as fast. Perhaps car 1 is texting. That's my pet peeve. Driving along, texting, not paying any attention to what they're doing. They don't notice they've come up on the rear end of car 2, so they rear end car 2. The result, besides mangled bumpers, car 1 will continue moving. So we're not talking about stepping on the brakes yet. We're just talking immediately to the collision and just immediately after the collision has happened. The bumpers have just touched. Car 1 will still be moving. Car 2 will still be moving. But will they be moving at the same speed they were moving at before? No. Car 1 will be slower. It will have slowed down a bit. Car 2 will have sped up a bit. So V2 final is bigger than V2 initial was. But V1 final is smaller than V1 initial was. Okay? So this is immediately before the collision happens. This is immediately after the collision has happened. If car 1's momentum changed, if its momentum changed, there was therefore an impulse. If there was an impulse, that meant there was some sort of net force applied for some period of time. You right with that? What force acted on car 1 to make it slow down? Car 2. The fact that it hit car 2. Car 2 pushing on car 1 made it slow down. Likewise, car 2's momentum changed. Its velocity is now bigger than it was. If its momentum changed, there was an impulse. If there's an impulse, there is therefore a force applied for some period of time. What force caused car 2's momentum to change? Car 1. So basically, we have force of car 2 slowing car 1 down, and we have force of car 1 speeding car 2 up. What can you tell me about those two forces? They're the same. They're the same in magnitude. They're obviously opposite in direction. So the force of car 1, car 2, doesn't matter which way we're at it, I suppose, is equal to the negative force of car 1. All right. Let's look at the impulse. For car 1, car 1 had a force. Well, let's just talk about these as average forces, so we can go ahead and say the average force times the change in time. It doesn't really matter if we write it as intervals or not. So car 1's momentum changed because the force of car 2 acted on it. So using the bottom equation, the average force times the change in time, the amount of time it took for that collision to happen, is equal to the change in momentum. So the force of car 2 times the amount of time that collision lasted, which wouldn't be very long, has to equal the final momentum of car 1 minus the initial momentum of car 1. So the force of car 2 pushing on car 1 caused car 1's momentum to change. So momentum final 1 means the final momentum of car 1. Momentum P1 initial 1 means the momentum initial for car 1. Car 2. Background music. Car 2's momentum changes because the force of car 1 acts on it. Car 1 exerts a force on car 2. That collision lasts some period of time. Well, force times time has to equal the final momentum minus the initial momentum. So the final momentum of car 2 minus the initial momentum of car 2 is equal to the force of car 1 times delta t. Okay. But, as we said, the force of car 2 is equal to the negative of force of car 1. So we can actually write this top equation as minus force of car 1, delta t, is equal to the final momentum of car 1 minus the initial momentum of car 1. So this is the same thing. We've just made this substitution. We know the force that car 2 exerts on car 1 is equal to the negative force that car 1 exerts on car 2. They're equal in magnitude, opposite in direction. Okay with that? Let's add these two equations. Force of car 1 is the same. Delta t is the same. However long the collision occurred for car 1 is how long the collision occurred for car 2. So this side, when I add it together, you get a big fat 0. On the right-hand side, I get final momentum of car 1 minus initial momentum of car 1 plus the final momentum of car 2 minus the initial momentum of car, initial momentum of car 2. We can write this also, final minus initial is delta P. So delta P, change in momentum for car 1, plus delta P2, the change in momentum for car 2, has to equal 0. I'll rewrite that here. Sorry, it's kind of low. That means, however much the momentum of car 1 decreased by is exactly how much the momentum of car 2 increased by. The momentum was transferred from car 1 to car 2. This is a conservation law. This is called the conservation of momentum. That's what we mean when we say the change in one quantity plus the change in the other quantity has to equal 0. As one increases by a certain amount, the other has to decrease by the same amount to maintain the equality at 0. Okay. This is always valid if the forces that cause the changes in momenta are internal forces. As long as it's just the forces that one object exerts on the other, and the other exerts back. As long as the forces involved are the action-reaction pairs, then this equation will be valid. This equation is not valid if we consider the time when these drivers step on their brakes and pull over to the side of the road. Because what would change their momentum then? The brakes, the friction with the road, the brakes, brake pads. That's not an action-reaction pair with the other car. So as you have external forces, such as friction or any other sort of push or pull, this equation will not be valid. This equation is valid only if the forces that are causing the change in momenta are internal, are action-reaction pairs between the objects in your system. Okay? Works fabulously for collisions, as long as you're looking only at the time frame for the collision itself. So not stepping on the brakes, not pulling over to the side of the road, just immediately before the collision to immediately after. The nice thing is, these forces are not easy to determine. They're not constant. The acceleration is not constant. These aren't easy to work with, but this really is. And this is perfectly applicable in a collision. So that's one really nice thing about momentum, is that you have a really easy way to look at a very complex system. Okay? It's nice. It works out nicely. This equation as well, so it works for collisions, all collisions, as long as you're looking immediately before the collision happens and immediately after the collision. But it works also for explosions. Because an explosion happens within the system itself. A firecracker, for example. It's the gunpowder within the firecracker that explodes it into a bazillion pieces. Because it's internal to the system, this still has to be conserved. So when you watch a fireworks show, you're now going to look at it differently. You're going to think about the conservation of momentum of all these fireworks, which hopefully doesn't ruin the show for you.
Way to go. Dang you.
I know.
Ruined the last bit of childhood innocence.
Now there are two types of collisions. As far as this equation is concerned, it doesn't matter what type of collision you have. This conservation of momentum works in every single type of collision. But this is going to be important a little bit later, the type of collisions. One type of collision is elastic. Elastic collisions consist of no deformation, at least no permanent deformation of your object, no heat, basically. So, like,
I get it.
balls hitting each other, like pool,
Right.
billiard balls. When they hit and come off, they still are balls. They still have the same shape they had before. So that would be pretty close to elastic.
So why don't we make car bumpers out of billiard balls?
Because the force of impact would be incredibly huge, and you'd hurt all the occupants. Technically, an elastic collision is characterized by no energy loss. We haven't talked about energy yet. We will in the next chapter. But that is what characterizes an elastic collision. Think about elastic bands, rubber bands. If you stretch them out, you let go, they go back to their original shape. So no permanent deformation. Technically, billiards aren't perfectly elastic because sound is a form of energy. So the fact that you can hear the collision happening means that some energy was transferred to another form. But it's so tiny, the amount of energy that was transferred, that it's okay to treat billiards as a form of an elastic collision. Another example would be bowling. The ball hitting the pins. The pins still are the same shape. The ball is still the same shape after the collision has occurred. So bowling would fall under this category. And again, you can hear the collision, so technically there's a teeny tiny bit of energy that goes into making the sound. But it's so tiny that it's pretty much insignificant, so we don't have to worry about that. The other type of collision is inelastic. Well, if elastic is no energy loss, then inelastic is energy loss. Now by loss we mean that it's no longer in the form of moving energy. So the energy that it had because of motion. It takes a lot of energy to make your bumpers look really crappy. Cars crash together, those bumpers get mingled up, bent in, lights get broken. It takes energy to do that. That energy cannot be retrieved and used for anything else. So we say that it is lost. Technically it's still energy, but it's not in a usable form now. So energy is not maintained like it is in elastic. By the way, there is a subset under inelastic. Perfectly inelastic. Your objects actually stick together. So they'll collide and catch on. So for example, football. You've got your guy running with the ball, someone comes up to tackle him, grabs him, holds on to him. That would be a perfectly inelastic collision. Okay? They held together. They stuck together, at least momentarily. Okay? The nice thing is, this equation is perfectly valid regardless of the type of collision we have. It's valid for elastic collisions, inelastic collisions, perfectly inelastic collisions. That equation works for every single type of collision. When we talk about energy, we'll be able to give ourselves another equation that works here. We'll be able to use the conservation of energy equation for elastic. That's what will be different. Okay, so I'm going to take our equation right here. Conservation of momentum equation. Delta P1, meaning the change in momentum of object 1, plus delta P2, the change of momentum of object 2, has to equal 0. To write this a slightly different way, I like to look at it a little bit differently. Remember, change in momentum 1 was momentum 1 final minus momentum 1 initial. Change in momentum 2 was momentum 2 final minus momentum 2 initial. I'm going to take all the initial values to one side and the final values to one side. So all the initials on one side, looks like this. The initial momentum of object 1 plus the initial momentum of object 2. This is the initial momentum of our system. So the initial momentum of every object in our system has to equal the final momentum of every object in our system. Now that doesn't mean the individual momentum, whatever car 1 had before equals what car 1 has finally. It means the total system. The sum of the momentum initially has to equal the sum of the momentum finally. So totally, however much momentum you have in the system initially, that same total amount needs to be there finally. It can flip-flop between objects, but it has to be there finally, as a whole. So that's another way we can write the conservation of momentum equation. It's the same equation, just written out a little differently, is all. So let's go back to our example here. Let's say we have car 1 traveling at 15 meters per second. Right the instant before it hits car 2, and car 2 was traveling, I don't know, 8 meters per second. Let's go ahead and look at it as if their bumpers, when they collided, their bumpers got stuck together. So they were stuck together. So they're stuck together. The collision has occurred. Their bumpers are mangled. They got so mangled that they got stuck together. So the cars would be moving at the same speed. They'd be moving together. You right with that? I'd like to know how fast they're moving. Okay. Well, this car is going to be moving slower after the collision than it was before. This car will be moving a little faster after the collision than it was before. Their momentum changed because of the force that they exerted on each other. So momentum has to be conserved. So if we find the total momentum that our system, okay, by system I mean all the objects involved in the collision. So our system involves car 1 and car 2. The total momentum of our system initially has to equal the total momentum of our system finally. Well, this car, its momentum now momentum is a vector. So what direction is the momentum of the car 1 in? To the right. Positive I hat. same direction as the velocity. Momentum is mass times velocity. So whatever direction the velocity is in is the direction of momentum. Momentum of this one. Also to the right. So the total momentum of the system $30,500. What are the units of momentum? Whatever we multiply together.
Oh, come on.
I know. Hard question. So the total momentum of our system, 30,500. We don't have a special name for this. Kilogram meter per second is kilogram meter per second. It would also be a Newton times a second. You can write it that way as well. It's in the x direction. Well, for a collision, as long as we're looking at immediately before the collision happens to immediately after the collision happens, the total momentum has to stay constant. If this is how much momentum there is before the collision happened, this is how much momentum there has to be after the collision happened. Okay? You alright with that? It has to be conserved. There's no external forces acting on it. The only time this is not valid is if there are external forces causing the momentum to change. So like friction, or drag, or some other push or pull. So this has to equal the final momentum, but the final momentum is the momentum of car 1 final plus the momentum of car 2 final. Since they're moving at the same speed, because we said they stuck together, that's the same as saying one object of a mass of 2,500 kilograms moving at some final velocity. So our final velocity is, oops, kilograms cancels with kilograms, leaving us with meters per second, which is good since we know that's the appropriate unit for velocity. The momentum was in the I-hat direction. The final momentum is in the I-hat direction. So the final velocity needs to be in the I-hat direction as well. So this means these cars would move together at a rate of 12.2 meters per second. It's faster than the 1,000 car was going, but slower than what the 1,500 kilogram car was going. Which hopefully makes sense. The 1,500 has to slow down, but it gives some of its momentum to the 1,000 kilogram car, which will speed up. By the way, if they don't stick together, you would need to know how fast one of those cars was moving after the collision. Otherwise, we would have too many unknowns.